our meeting of the Baltimore, Washington chapter of the Health Physics Society. And we're thrilled to have to see a good turnout. I'm seeing around to 22 people here online. So I hope this is going to be a fascinating talk today. And just for a few minor updates on logistics, please make sure that you mute your mic so that the speaker can continue with the presentation. And we'll have a time for a Q&A session later after the talk, so we'll give more time for people to talk. My name is Bamnat Alamayo. I'm the current president of the Baltimore, Washington chapter of the Health Physics Society. Um, and before I introduce our speaker tonight, I have a couple of reminders about the chapter activity. So the first is to save the date. So our annual meeting of the chapter is coming up. It will be on Friday, May 8th at the Ceviches, Magianos at Ceviches, and we'll send out the details soon. Uh, our member Kathy has worked hard on the details, so we'll announce that, and also the registration and other details will come soon. The second reminder is membership dues and registration. So I think it's now a perfect time to register and renew your membership. So if you haven't paid your dues for the current year, you can do so through the website. We have a discounted member rates for all of our upcoming meetings. And for membership, we have a $20 membership for a 1 year membership and a discounted $50 for a 3 year membership. So you can head to the chapter's website to get advantage or to take advantage of this membership and to make sure that your status is up to date. Saying that, now it's my distinct pleasure to introduce our speaker for today, Mr. Benjamin McGee. So Ben currently serves as the Assistant Director for Radiation Safety and Radiation Safety Officer at the University of Maryland, College Park. His career path in health physics involves an interesting path. So previously, he spent over a decade as a senior scientist within the RADCON program at the Nevada National Security Site and was with the Department of Energy's Remote Sensing Laboratory. Another exciting career path that I found is Ben has served as the lead health physicist, radiological engineer, and astronaut dosimetrist for two major firms, Bigelow Aerospace. He was responsible for the inflatable module currently on the International Space Station, and Axiom Space, which has successfully conducted 4 private astronaut missions to the ISS. Uh, Speaking briefly about his academic background, he has a BS in geology from the University of Wyoming, specializing in infrared spectroscopy of planetary surfaces, and MS in space studies from the University of North Dakota, where his research is focused on the effects of ionizing radiation on asteroid surfaces, better known as space weathering. Ben is also a member of the Health Physics Society, the National Register of Radiation Protection Technologists, and the American Institute of Aeronautics and Astronautics. He is also a National Fellow of the Explorers Club. So Ben, we are honored to have you with us today and to share your unique expertise in the intersection of health physics and space exploration. So as you see from his slide, his talk is Health Physics Challenge in the Age of Commercial Spaceflight. And if you have any question, let's save it at the end, or you can post your question in the chat and we'll address later. So Ben, the floor is yours, and thank you again for joining us tonight.
Excellent. Thank you so much for the nice introduction. I want to thank Femnet and the local chapter of the Health Physics Society and Dan Blumenthal who reached out to me for inviting me to give this talk. Is my audio coming in okay?
Yes.
Okay, great. Then I will proceed to the full version of the screen here. All right. So what are we talking about today? Well, as was briefly mentioned, I've had the fortune to work in a very niche industry and apply our field's expertise in a new and exciting arena, but it comes with distinct challenges. So this is a technical talk, but it's not going to be a technical talk in the way that you think, and I'll get to that. So this is the obligatory talk about what we're going to talk about slide just so you can look down the road a little ways. So I'm going to talk a little bit about why am I here? Why are you listening to me? Um, a little bit on space weather. I'm going to go fast. This should be breezy. This is not going to be hyper technical, but then we're going to have to dip our toes a little bit into some rocket science. And then we'll talk about the bizarre regulatory landscape right now for commercial spaceflight with people. And then how do we, as health physicists, plug in to bringing good radiation protection strategies to commercial spaceflight. And it is non-trivial and it is strange. So I'm excited to give this talk. I don't think there's ever been a talk like it, and we'll get into it. So yes, I'm currently serving as a radiation safety officer at the University of Maryland College Park. My career has been torturous, and I've had the opportunity to brush into some interesting things. But specifically today, yes, I ran the crew systems program, and I did all the health physics, and we call it radiological engineering in terms of the shielding analysis, space weather forecasting, dose forecasting for Bigelow Aerospace. And this is a picture of the Beam spacecraft. It's the Bigelow Expandable Activity Module. And Bigelow Aerospace, believe it or not, they're no longer an active company, but the module is still on the space station, and their technology was expandable spacecraft, inflatable spacecraft, which didn't mean they were flimsy. When people asked, how can you, is it like a balloon in space? Is it going to pop? And I said, no, you fill up your car tire and kick it real hard, you're going to break your foot. You're not going to hurt the tire. So that's the same. That is also inflatable, and in this case, the spacecraft technology held up well. Its advantage is its ability to crumple down, and you save space in a rocket, and then it inflates to give you more volume on orbit. But that also means you had to have walls that were thin enough to crumple. So there were some radiation challenges associated with that. And then Axiom Space, while I was at Axiom, I did all the dose reconstructions for 12 private astronauts, non-NASA, and which brings this all into completely new territory. They've flown another four since I left, so they're up to 16, and that makes what we're going to talk about all the more interesting. So I think this means I've got a monopoly on health physicists who are inside commercial space station ventures who've flown people or modules. So far, there's been nobody else. So I have a unique vantage, and I really want to pay forward what I've seen from the inside because I really think I would be shocked if anyone had heard some of or had encountered some of this before. So I'm not going to talk about the health physics challenges we already know about in the space environment. Particle detection, the variety of particle types, the fluence, how do you get an instrument response? How do you deal with secondary radiation interacting with the spacecraft? The problems of dose reconstructions, how do you shield this stuff? That's not really what I'm going to talk about. I want to convey the realities of integrating health physics into this stuff that may shock, surprise, confuse, or consternate you who may be future health physicists who find themselves in the work. So if we're being very optimistic, if more and more people go out to space and the market really opens up, we're going to have more of these challenges, not fewer with time. So I see this as a potential, growing market for health physics. So a brief crash course on space weather, just so you have a sense for what we're talking about in case you haven't had any heliophysics background. Um, what I like to say is if space is a sea, radiation's the water. And why is that? Man, I really thought I got rid of all these transitions. Sorry about that. Anyway, um, well, the stars, right? Every single star is a giant gravity-driven thermonuclear fusion reactor. And so we've got a cosmos just, littered with nuclear bulbs. Um, there are two main types of space radiation. I call it the obliterated stuff of the sun. And I call it a charming rebrand. What is all this stuff that's there? Well, you've got what's the sun made out of? It's hydrogen, and when you ionize the hydrogen, you've got half of its electrons and half of its protons. So the solar wind is just a stream at about 400 kilometers per second of electron radiation and proton radiation flying all throughout the solar system. And then the other half of space radiation is particles flung off by all the rest of the exploding stars. And there are people who might quibble. There are other processes that can accelerate gases, so you can have accretion disks around black holes and exotic things like that. But it's earnest to just think about the you know you've got the stuff from our local stars and the stuff from distant stars. And we call that a misnomer as galactic cosmic rays. GCRs, they're not rays, they're not photons. But that harkens back to the way back when scientists first discovered high energy interactions and had no idea what the radiation was or where it was coming from. And unfortunately, the name stuck just to confuse everyone I try and talk to who's not already a health physicist or an astrophysics, background type. So, I mean, if I could wave a wand and change the world, I'd call these all ISPs, interstellar particles. That's actually, it's actually what they are. And unsurprisingly, they too are almost all protons and electrons for exactly the same reason. There are fractions of heavier elements because what are the stars doing? They're taking all that hydrogen and helium and smashing them into heavier and heavier elements. So, about that proportion with the amount of time that all those ovens have been running in the cosmos, yeah, you've got a smattering of iron and oxygen, and you move up and you can get some very heavy elements when stars explode. But by and large, it's about the same. So that is what we're dealing with when you go out of the Earth's influence, and especially out of the influence of the Earth's magnetic field. So if you weren't aware also, the proportion of the incidence of these radiation sources shifts with time. I like to call it, you can think of it as cosmic tides. And the reason for that has to do with the solar cycle. So, if you were really trying to break this down into common parlance, you could call the radiation from our local star space radiation rain, and the stuff from the rest of the cosmos more like radiation hail. It's typically got a little more steam to it. Um, and you can have occasional tsunami, I think is a very good analogy when you have a solar particle event on the sun, a coronal mass ejection, because we don't actually know, in case you ever find yourself having to explain this to someone, um, much like when there's an earthquake at sea, a large one, we know that an earthquake happened and we know that there is a tsunami possibility, but we don't actually know if a tsunami is going to hit us until we see local buoys actually go up and down on the water and track the wave height. The system is too complex to really know with certainty whether or not a tsunami is coming. The exact same thing happens with the sun. When there is a large event on the sun, it's just like an earthquake at sea. We know that it happened. We know that there is a radiation wave that could strike us, but because of a lot of nuances of the interplanetary magnetic field and things like that, uh, it's not guaranteed. So by the same token, it's a you can think of it as a space tsunami warning, but just an anchor point to think about. So, and something else I want you to think about is, okay, now we know what when you leave the Earth, you're dealing with space weather. This the charming rebrand, solar wind. So electrons and protons and a smattering of alphas and heavier stuff up to iron. So what is this? What is this doing? And if we return to this, space is a sea, rad's the water. Um, if we're going to put ships out there, we want to know what the water does to the ships, to the boat. So this, you could think of this as a material science problem. So recall that the radiation we deal with is ionizing by and large, if we're not, no offense, laser safety officers out there. Um, but take a perfect crystal lattice. All the molecules are nice. They're bound in a regular structure. And when you break the molecular bonds as they are, you start to glassify the material. And if we lean into the geophysics world, they have a term for that. It's called mictization. So it's the act of turning something into glass. So what's happening as the ionizing radiation that we see in space, particularly the protons, high LET stuff, it's bouncing through and breaking these perfect crystal lattices and slowly turning the material into something more like a glass. And what does it do? You can really honestly think of this as very small scale micrometeoroid impacts. This was something that high velocity impact testing, people who fire gas guns at windows for space to see if they're going to break. The same sorts of things happen. You have pitting in molecular surfaces, you have displacements, you have holes, you have things that are jammed in there, and they cause the entire structure to shift a little bit. And what you'll get is grain creep. You'll get weaknesses in your material. You get materials properties start to change. And one thing that I hope not everyone before, because I think it's so cool, and I want to be the first one to show it to you, is another slice from the geology world, literally, uh, which is zircon damage in silicates. So what you're seeing here is zircon crystals in the center. This is a thin section of rock, so rock sliced so thin you pass light through it and it's filtering. You're looking at it under a microscope. And in the center of these dark areas is a zircon crystal, which is naturally enriched in uranium. And so you have all the daughters coming off the uranium decay chain, and what you're seeing is alpha radiation damage. And the radius, so slowly, as you have destroyed the crystal structure, light has a really hard time getting through it because there's no order. So it's like having a bunch of polarized lenses sitting on top of each other. It'll just start to look black. And that's what a glass looks like when you look through polarized lenses in thin section. And so you're actually seeing this type of radiation breakdown in materials with your own eyeballs, which I think is impossibly cool. And if you really, really get into this stuff, you can actually see slight differences in radii of the darkening, and you can attach that to which alpha you're actually seeing. Is it the polonium? Is it the radium? Is it, it's pretty fun. One of the coolest images perhaps ever taken is this, which is the same idea. There is a zircon dot in the center of a sapphire crystal, and the image on the right is a radiation damaged sphere. You're seeing what look like bubbles. Those are all defects in a sapphire crystal. So it's a three-dimensional version of the radiation damage. And all this is to just paint in your minds a visual of what space radiation is doing as soon as you leave Earth to any materials that are going out there. So the molecular integrity starts to break down. It starts, if you left it out there for a very long time, you would glassify materials. And like I mentioned earlier, that has a lot of practical impacts, like changing the electrical properties of silicon. You can cause bit flips and upsets, of course, which if you've dealt with electronics in space, you know that that's a major radiation interaction problem. But also, like materials around nuclear reactors, you can have neutron radiation breakdown and damage of alloys. And indeed, the exact same thing starts happening to materials in space. Even soft goods, things like Vectran or like Kevlar, they will fail faster under proton bombardment than you would think they should. And even when they fail faster at the same dose, most failure testing was done with gamma radiators. And unfortunately, if you think about it, it makes sense. Gamma breakdown is stochastic and it's spread out through all the material, but proton breakdown is directional. And so Vectran actually fails faster at the same dose of protons, and we're just learning that stuff. So all this to say, all right, we go to space, things start breaking down. What does this do to people? Well, I challenge you to now intentionally take that same visual of the alpha damage and the sapphire crystal and now put a biological system there. So we know about radiation carcinogenesis. We know if you get enough radiation, you have, you know, um, acute radiation syndrome. But what started to be revealed over the last decade and a half or so is the rest of the biological systems in a human being are starting to get broken down. The central nervous system, the cardiovascular system, the cognitive, there you can induce dementia-like effects. They're starting to do this in rodents, and there's starting to be some synergy with proton cancer therapy. And so, again, I said this is not necessarily surprising when you think about what the environment is doing to raw materials. And so this is a breakdown of sort of the state of research. Well, it's a spectrum of effects, right down to the things that I think are understudied because they're in a way less severe or more mundane. But cataracts and melanomas are going to be really exacerbated by secondary radiation as the primary comes in and hits the spacecraft, hits heavy elements, and then breaks down into lower energy metal ions. Well, that's going to be really good for being absorbed by people because we've slowed it down. I actually have a slide on that. So again, this is just to paint a picture. What's happening? This is really truly a health physics problem. So how energetic is this stuff? And I'm not gonna I could rattle off, the energy spectra and what we're measuring, and I want to come at this from a different direction. An anchor point you can put in your pocket. So we know it's generally high LET. We know it's penetrating and energetic, but how bad is it? How bad is it really? Think about if you're building a spacecraft. What does that mean? Can you stop it? What would you need to stop it to actually shield it? Well, let's go to the Apollo missions. And one of the things that I think people never think about, one of the reasons we took the lunar core samples was to see the depth of radiation damage through lunar regolith and the lunar surface. So how much lunar rock does it take to stop everything, even the high energy CR, just to go all the way down to stop 100%? Well, the answer is 3 meters. So we see passive molecular radiation damage in mineral samples to a depth of basically 10 feet below the lunar surface. So the majority of it is going much slower than that, but there's a small fraction of high energy stuff that's stuff that's really truly the hardest to slow down and stop. And if you want to stop it all, you need 10 feet of solid rock. And then whatever the equivalent would be if you wanted to use a smarter material like water or high density polyethylene, it'd save you a little, maybe 8 feet of poly, but you're still talking about an enormous problem, a huge amount of mass. So that's the scale of the issue when we walk in the door to a space company to help them put good health physics, and they go, "Hey, isn't there some kind of like special coating we can put on the walls to like stop all the radiation?" And you're going like, "Oh boy, how do I explain this?" No, you need an asteroid to stop everything. Um, and a shielding nuance. A proportion of the radiation out there is so energetic that actually it'll go through one side of the spacecraft, through an astronaut, and out the other side, and only deposit a little bit of energy on the way through. Um, you can actually, there's a penalty if you have a heavy element like an equipment rack with a lot of stainless steel in it, and the same radiation comes in and hits a chromium atom in there and then turns around and sprays a shine of they've effectively down converted that very fast penetrating radiation to something slower. And after all, humans are mostly water and they're great at stopping that sort of thing. So you've gone and taken what would have only been a fractional dose in terms of energy and down converted all of that energy and then spread it out across your skin or shallow certain where you could really have melanoma risk shoot up and things like that. So just to paint in your mind, this is not a linear problem when you're trying to integrate. All right, hard stop. Uh, the rocket equation, and I say versus health physics. So that's the environmental part of the problem. A little bit of rocket science. This is the Tsiolkovsky rocket equation, a little more than a century old now. It's a mainstay of spaceflight. Um, we don't actually have to go through it. What does it tell us? It tells us the amount of fuel you need in terms of the change in velocity necessary to go as fast as you want. So for a certain amount of payload, you need a certain amount of fuel so that when that goes away, you have a change in your exhaust velocity, and that gives you your change in thrust for the payload. That's great. So you can calculate how much do you want to launch and how much fuel do you need to get there. Cool, except we'll now consider that fuel also payload. You need fuel to launch that first fuel to space. It has weight. And okay, fine. So you need to add a little bit more fuel to launch the fuel so that you can launch the payload. But wait a minute, that fuel has weight. So you need to add fuel to launch the fuel to launch the fuel to launch the payload. So what's the practical effect of this? It's called the tyranny of the rocket equation. It means teeny tiny changes in your payload mass up top equate to huge burden in terms of so a tiny increase in payload mass equates to a huge change in fuel and weight necessary to get that to go up. So what does that mean? That means that since spacecraft have been built, the mantra has been less mass. And well, we've just spent our time learning to understand that in the space radiation environment, you've got things like exploding stars and nuclear reactors that are shining all the time. And you need lots of attenuating mass to actually try and stop it. So you can expect, as a health physicist walking in the door in a space company, to be like a salmon swimming upstream. There's you, and then the rest of the spacecraft development program is taking things the other way. They're trying to make it lighter, faster, thinner, cheaper. So this is my visual at the space companies where I have worked. There is the entire space company chanting less mass, and I'm the one guy in the corner going, more mass. Um, so it puts us in a very interesting situation. And so that's one thing I wanted to paint is this is the environment that awaits you in the commercial spaceflight world. And so now the regulatory rabbit hole where no regulator has gone before, and the Trek pun is apt because all right, let's talk shop dose rates. So the average dose rate in low Earth orbit, it's about 100 milligram a day, 1 millisievert a day. So what does that mean? Yeah, amortize that out over a week. It means for all intents and purposes, space is a radiation area by the numbers. So cool. Well, if you're going to enter a radiation area, you need to be a rad worker, which means you need to have dosimetry and monitoring, and you need a radiation protection program. And that's great. Um, but are commercial astronauts radiation workers? And we're in the sticky situation now where no one is generating the radiation that the astronauts are being exposed to, its background. And we're not in the US traditionally in the habit of managing background with little asterisks for radon exposure at work. And there are a couple instances, but by and large, including the FAA, so far. I mean, in Europe, they do manage pilots as a type of radiation worker and flight crew, but we don't do that yet. So, So where do we go from here? Who decides? Well, OSHA. The Occupational Health and Safety Act says that if no one else is doing it, it's OSHA's baby. But now that we're sending people out to space, the legal conversations that are occurring declare that OSHA has no statutory authority to regulate private activities in space, except NASA went to OSHA in 82, I think it was, and they signed an MOU for there's an extraordinary circumstances clause in OSHA's radiation protection, which is now outdated, but their radiation protection regulatory wording. And so NASA has permission to create their own bespoke dose limits, but that only applies to NASA employee astronauts. Okay, so it's not NASA, and it's not OSHA. Who has the statutory authority to regulate safety in space? Aha, FAA. FAA has an Office of Space Transportation. Cool. But wait, they actually testified to Congress in 2017 that nope, it's not theirs. They only regulate launch and reentry, not like passing through the atmosphere, not while somebody's actually out in space. You go, okay. So who's got the statutory authority to regulate commerce in space then? It's the Department of Commerce. They have an Office of Space Commerce. Um, and they have been given regulatory authority to regulate payloads, commercial payloads in space, and they are responsible for tracking for collisions and the stuff that NORAD used to do. Department of Commerce is taking lion's share of. So this might be their ball. But I will tell you, they have not even started to think about picking up humans as a type of payload during an orbital flight phase. So nope, they're not doing it. So here we are. This is the regulatory. So FAA has the ball for rad safety going up and down, but not while you're there. NASA has regs, but they're in their own bubble. Department of Commerce has authority, but they're only doing like satellites. And OSHA, well, they might, but they don't have demonstrable authority and they're not doing it. So truly right now, it is a whole. So the regulatory environment for radiation safety for commercial asset, the 16 people that have now flown with Axiom, who are not under their own respective international, there were a few international folks who have their own regulatory authorities that they fall under. They're unregulated. So, what does this mean? This means when you are a working health physicist in the middle, you are trying to get good practice into your program. You will not have any regulatory support behind um, dose limits or ALARA initiatives. It is the Wild West. So I would say, what should you expect? You should expect to try and find other reasons to sell radiation controls to the program. So things like buying down future litigation risk. We all know that people are terrified of rad by and large, and we all have a 44% chance of getting cancer. And so some people are going to fly and they're going to come back and get a cancer, well, have a cancer discovered shortly thereafter, and then point straight to the space flight, which all of us know the latency time won't match, everything won't match, but you have to prove it. Um, so if you have a good monitoring and dose limit program, you get that also helps stand up your case. Or increasing the lifetime, you might have to point to, it's unfortunate, but to things that aren't the people. You might have to look at overall dose limits and say, oh, this is good for the people, and it will make your experiments and equipment last longer. That might be the spoonful of sugar that helps the health physics medicine go down. And there's a marketing angle that I had to work, which is this could be a thing that makes us better than the other guy, so to speak. So, you could, if you are going to fly with NASA, for instance, where they do have dose limits, they could pay to fly and fly more missions with us if we have a lower dose environment than the other guy that doesn't. So it's an interesting thing to have to spin in your mind, but um, there you go. That's the strange regulatory space. So how about radiological engineering for space? Well, I think most of us are familiar with neutron shielding, right? You want low Z materials, water, high density polyethylene, borated stuff. Great. Um, but I was surprised that even though NASA astronauts go through, there's a space radiation analysis group that go through a lot of training. Well, we had quite a few pros between the two companies that went private after they retired from NASA, and all of them were surprised when I told them that the windows are actually the best shielded spot on the space station. You've got, the skin of the modules is less than a centimeter of aluminum, and the windows are like 4 inches of solid Lexan with the shuttle, or you got silicon dioxide, you got borated, high tempered glass stuff. It's great compared to the little aluminum shell. And that is absolutely not like they were avoiding. They thought that Russians were getting high doses on the Russian segment of the space station because they had windows in their crew quarters, not because they were pressed right up against the thin skin of the module with no supplemental shielding at all. So there's this culture where they sort of blame the windows for letting the radiation in, and it's completely the inverse. Um, so there's that, but then at the system design level, so we spend a lot of time when we teach about what shields neutrons, and it's the same thing for space radiation if you're dealing with primarily protons that are penetrating. You got your key things: water, high density polyethylene, plastics, and we may have done too good a job because then these engineers who are not health physicists, they walk away going, all right, it's water or nothing, or it's plastic or nothing. And they think that there's something special about it that's, particularly it's unique in blocking radiation, not that it's just more efficient at blocking radiation. And so I had to spend a lot of time explaining lower Z is always better. So we'll take what we can get. Like aluminum is way better than stainless steel because of the nickel and the iron and the chromium. You get the not only the mass and volume penalty for the same effective amount of shielding, but there's also your secondaries, which are I say high energy secondaries here. I'm being really loose with the terminology, but lower energy. But I think you see what I'm saying. Um, there's a spray that you'll get off of the stainless that you won't get off the aluminum. Well, you'll get some neutrons, but um, so what did I find the health physicist's role is for radiological engineering? It basically lurk around the entire space enterprise. And I was able to because in order to do any large scale modeling of the dose environment, I had to know what everything was made of. So you'll have a reason to talk to everyone, but while you are doing that, you can make gains one-on-one by just explaining, hey, can you use carbon fiber here instead of aluminum? Great. Can you use aluminum instead of stainless? Great. Can you use silicon for something? Great. Like just try and move things down a little bit. And I call that the Z footprint, the overall kind of proton footprint. So you want to bring your spacecraft's Z footprint down. And I think if you think about it like that, if you make wins throughout the spacecraft, you can slowly improve the over, or things like popularizing the idea of a high density poly finishing layer on the inside that has a good chance at catching a lot of the low energy secondaries before they can get to the astronauts who are in the habitable volume. So, and then another thing is know your design reference mission. This is jargon in the space world, but what is that? What's a DRM? Well, there's a temptation if a company's trying to build a space station, there's no huge market for this right now. So they really want to be able to build a space station and serve whoever wants to buy something. So if somebody or some government wants to fly a crew of four for 6 weeks, great, they want to do it. They want to fly a crew of two for 6 months, cool. Do they want fewer or more contingency supplies? Whatever you want, 30 days, great, 90 days, great. Whatever you want to pay for. However, this is all nice on paper, but let's take one module I got to know intimately well is putting it mildly. I built hundreds of versions of this in model space because this was a large version of that beam module. It was supposed to have 330 cubic meters of internal volume. And however, what were we contemplating simultaneously? Well, we can have one of them parked on the space station, or we can have two of them parked together that are up at a higher altitude, or we can have a station on a propulsion bus, which could actually travel to, Lagrange points, or we can have partner with United Launch Alliance, and they've got a new rocket. We could put one of these around the moon, and it'll work as the NASA's gateway, or we could actually land some on the moon, or land some on Mars. And in management's mind, this is just applications for the same product. But from the health physicist vantage, we're married to logistics and maintenance. Why? That's the bulk of the mass that actually goes into these modules. The food, water, other consumables, stowage, replacements, how much and where this goes will pretty much define the radiation environment of any spacecraft. So if I'm trying to model, or one of you are trying to model the interior of the spacecraft, that design reference mission, do you have 90 days of supplies or 30 days of supplies? Are you going to drink your radiation shield if the ship is waylaid by a storm? And then the dose environment's totally different. If you're in LEO or high altitude or Lagrange point or orbit of the moon or on the surface of Mars, you got backscatter neutrons and, you know, uh, everything is different. So the punchline is from the health physics perspective, the B330 in each of these different scenarios is a completely different spacecraft. So that's what needs to be communicated. That at least if for no, and I would argue it's that way for the poor logistics guys too. We ended up partnered up a lot because they're like, we can't, we have to do everything differently if we're going to have 90 days of stuff versus 30 days of stuff. Um, but what I like to say is if you're designing to everything, you're designing to nothing. And in order for health physicists to be able to do their job, we need to actually know what the target is. So you gotta pick something. And then finally, the last part of what I learned is spacecraft requirements. If you're not in there, then you're not anywhere. And what do I mean by that? Spacecraft development lives and dies by requirements, and it follows a predictable process. This goes back to Heritage and NASA. There are variations on a theme, but generally, the process looks something like this. You start with what they call an SRR, System Requirements Review. So you pick your requirements here at this step. So you're moving off the whiteboard. What kind of a spacecraft do we want to make? And then, okay, what does it have to do? You pick your stuff. Then you work on that for a while and you hit what they call PDR, preliminary design review. That's when you have your requirements. Like, all right, this is our idea for how we're going to meet the requirements. And then everyone has a chance to review that. There's a big meeting with the chief engineer and scientists and everyone, and they poke holes in it. And then great, you go back and you work on whatever the after actions were. So presuming that approach was okay, then a few months later you have a CDR, concept design review. That's where you actually say, okay, based on the requirements and our approach, we want to use this hardware. Either we found it or we're going to build it. And you show the designs and everyone has a chance to critique. And then you get past that and the only next step after that's a manufacturing readiness review, like permission to go like bolt all the stuff together and build us a flight unit, and then you go. So why am I telling you this? Well, A, if you're going to integrate, it's nice to know how this really works. But the really important thing is the HPs need to get involved at the SRR, or you are going to have a heck of a time getting into any part of this spacecraft. You're going to be running around, smashing your head against stuff, but there literally won't be parking spaces for you to integrate your work. And by this, I mean, you really need to be working with the chief engineer, program management, chief medical officer, so you can get consensus buy-in for adding an ALARA requirement. So that gives you, as the health physicist, a seat at the design table. You need to have a requirement for dose limits. We don't have regulatory backing, so this needs to be negotiated, but having these limits is what would give you teeth later for getting shielding into the design. And then you need to actually have a shielding subsystem. You need to get with engineers and figure out how to put shielding to meet your dose limits into the spacecraft. And then finally, a monitoring subsystem. You actually need to define requirements and a chance for this to get into the overall program, so you can alert to poor radiation conditions, and you really need that for dose reconstructions to calibrate your models. And like, good luck getting permission to fly more pieces of hardware late while everyone is, three-quarters of the way down the track. And you're like, oh, I forgot a subsystem. Can we go have an SRR and a PDR and start all this stuff from my little subsystem? It gets really difficult to find spaces, and also things like the caution and warning panel. If there is a solar particle event and you have a radiation monitoring system, well, you might assume the system will just take care of taking the output from your monitor and sending it to an astronaut caution and warning system. That is absolutely not true. And so no one's going to think of it or fight for it except you, the health physicist, who will suddenly find yourself in a sort of an engineering hot seat. So you've got to reach out to figure out who's doing the caution and warning panel and tell them, oh, by the way, you need to add a little box for my system, or else you'll turn around and there's a whole caution and warning panel built and approved, and you're like, wait, I need to add something to it, and it's too late because it's already been through the process. And then one aside, there's actually, I would call it, a health physics culture warning with NASA. It came as a surprise to me to learn that in the NASA tradition, um, radiation safety is owned by the medical team and the chief medical officer. And that's contrary to my experience. I mean, I think those of you who've worked emergency response or with hospitals, I think out here down on Earth, if there's a radiological event, I'm used to the medical community going, we don't want it. Like, I mean, I'm not talking oncology, but I mean like some sort of contamination event or exposure event. They're like, tell us what to do. DOE, what do we do? It's completely the reverse. So I ended up stepping on a lot of toes because I was just doing health physics, and it was happening without the chief medical officer, and it caused me a lot of trouble, because the expectation was anything that had to do with crew protection would go through medical in the space world. So all that to say, oh yeah, after I lost the turf war, I had some flight dosimeters I've been working to fly for years, deprioritized flying to the space station in favor of some razors and stethoscopes. And I think that's the lessons learned from us in the commercial nuclear world back in the 80s and 90s, where we really need mainline access to management and our own pipeline to make sure that good, essential safety equipment and things are prioritized the way they need to be. But that hasn't happened yet in the space world, and it's all packaged together under medical. So fair warning, if you are interacting with commercial, or you should check if commercial space staff are coming from NASA, you really should have a conversation about the perception of program boundaries and where the lane stripes are, which will help you avoid future conflicts. And final thoughts. Uh, so take home points. If you get involved in a commercial spaceflight project where, with people, so there's health physics issues are in play, you're going to be swimming uphill trying to get shield mass allocated for launch. So start selling the need for it early. Um, a lack of current regulations, like I pointed out, means no one there actually has to listen to you. Not at all. So you got to really think of interesting ways to justify ALARA and dose limits on their own merits in the context of the other space risks. It's a different kind of argumentation than I ever had to do. And I worked in a few, I thought I had some challenging fights before, but this was some of the steepest climbing I've ever had to do as a health physicist in selling health physics. Um, you got to explain to the program that you need a firm design reference mission. You need to know, like, which spacecraft am I designing to perform sensible modeling. You can't take a model on the surface of Mars and expect you to give good numbers for Earth orbit or vice versa. So helping explain that, I think, will help the program help you not waste everybody's time. Um, and then you got to get health physics requirements into the design process at or before the system readiness review phase of development. So the odds of success go down the later in that overall design process you start. And the greatest successes that I found was actually pounding the pavement and developing relationships one-on-one with design engineers for specific systems and helping them understand lowering that Z footprint would improve the overall radiation environment of the spacecraft. So if everyone was trying to add improvements, then everything was getting better in a way that was also not showy in a good way. It's not like I was asking for 200 pounds of polyethylene while everyone else is fighting to trim out a pound here and a pound there to make their launch mass. This is something that could happen at the system level, and if you're improving material performance, it might actually save that system a little mass too, while it's smarter material. And then please coordinate with the chief medical officer to smooth out any cultural mismatches. It really hurts when the turf issues surprise you late in the process. And I think that's time. Thank you very much.
Thank you so much. It was a fascinating presentation. Thank you. Thank you so
Of
much.
course.
Yeah, we'll now move to the Q&A session. So let me start with Kat. Yeah, sorry if I messed up the order, but Kati first and then Bill will go second. And if you have any other question, you can also put in the chat if you can't speak. But Kati, go ahead.
Thank you. Great presentation, Ben. I have a question where you were talking about addressing ALARA and given the updating of ALARA regulations in quotes, air quotes, through the
Yes.
NRC and also through DOE because DOE has taken a swipe at it too.
Yep.
And then they hopefully, being past DOE employee retired, hopefully they would work together to come out with a plan. That always doesn't always happen. But what effect is that going to have on future space concerns?
Yeah, it's a great question. I mean, I could see there's enough institutional. So who would we talk about that affecting? First, NASA. So they've got a standard, an old standard 3001, which has been updated, but ALARA is a line item there. So if they're dealing with higher doses, and I think there's a high likelihood that would just remain because they're in a different dose regime than just your standard rad worker stuff. So I don't see NASA stripping that out per se. Although I will say that NASA has already been relaxing that a little because they can't meet their own dose limits for a Mars mission by and large. So they're already looking at a waiver process. So it may not affect NASA, but at the same time, NASA hasn't been terribly beholden to the Alara paradigm just because of the nature of their their mission. Um, in terms of commercial world, this is where it could hurt because since things haven't been formalized yet, they're really like there's going to be strong industry pushback about any new regulations that have to get incorporated. So I could see lobbying coming in from people saying, look, if we don't have to do this, let's not do it. Let's just people just accept the dose they get. We'll give them an informed consent thingy. I mean, there are already medical folks I've worked with who are talking about that. Let's just have them, the rocket could blow up. So let's just have them agree to get the dose they get. That's fine. So I think the strategy here for us in this environment overall, our liability is also our asset. Because it's not formalized, we have the opportunity to say, look at how this can benefit you. And we can give them, that's what I did, give them scary examples of companies that were really hurt or cratered by lawsuits that were not technically justified, but you still had to go through the process, and people are so terrified they'll just assume, it could be very damaging to say, oh, these people, in the narrative, these people are throwing people out into space, being exposed to cosmic radiation with no protections. I mean, it could shut whole companies down. So having an alarm program is the only real defense, I think, to that sort of civil threat to a company on long time scales. So that's my hot take.
Thank you. Bill,
Ben, good to see you,
Hey,
man.
how's it going?
Good, good. I would tell you that was an amazing talk, but I knew that coming in since I saw you were
Oh,
speaking. So anyway,
thanks,
so I
man.
have two questions. I'll ask one and then I'll get back in line. So in the commercial side of things, like where there's a vacuum, excuse the pun, the have you encountered like what's what have you discovered is the best sort of strategy for convincing people that radiation protection needs to be done? Is it an appeal to health? Is it an appeal to economics? Is it just doing the right thing? Is it legal for liability? I'm curious what your experience has been, and maybe if there's any contrasts to dealing with NASA on that front. So,
Sure, sure, sure. A great question. It's not been ethics haven't really that hasn't been the successful route. It's been economics and legal. And the reasoning there, I can't fault the rationale entirely because from if you're program management in any of these companies, they're hearing the chief medical officer say, well, as soon as you hit space, your body starts dissolving your bones, eating the proteins out of its own organs. Your eyes permanently change shape. Your brain is doing strange things with fluid volume, which may never go back to normal. So there's all these things that are serious medical risks that are happening just from being in a microgravity environment. And the longer you're there, the worse it gets. So it's very hard I found it very hard for me to just say, well, the radiation's bad for you, so we should do something. And they're like, yeah, so is everything else out there. Why should we spend more money? Because what can we do? Well, we can either do administrative controls or engineered controls. So we either try and make people fly less, which costs the company money, or we fly heavy shielding, which costs the company money. And so I had the only successful narrow path that I found was a combination of this legal plus economics, which is it is advantageous. People are scared of rad, so they could sue you. So you want to have a solid program. And also, you can make the other guy look bad first. If you have a good program and you start selling your, enhanced protection environment, more than the other guy. And then actually, the most traction, I think, was from biological experiments because many of those are very susceptible to the radiation environment. And so the calmer you can make that, the better data they could get. And that was some of the high dollar potential payloads that were worried about getting any useful data at all with so much radiation flying through, either affecting the biology itself or the detection mechanisms. So, yeah, great question.
interesting.
There was no easy path.
thanks. Let's go to William next, and then we'll move to the chat questions.
A great talk. I have two questions,
Thanks.
and I'm happy to have you answer the second one after Bill's second question. Again, great talk. I'm curious because of the very high RBEs for cataracts.
Yes.
Were the 16 people scanned to get baseline levels and set up in a monitoring program for later screening for cancer or cataracts? And the second question, which again you can address after Bill's second question, if foodstuffs used for shielding are consumed, what is the replacement?
Great questions. So the answer to the form, I think I can still talk about this without giving away anything I shouldn't be giving away since I don't work at Axiom anymore. Yes, one of the major, I could take a big step back and say some of the messaging I got, this answers your and Bill's question actually. Some of the pushback I got from the medical folks was most cancers are treatable. So if we just increase screening and we catch cancers early, then they wouldn't be fatal in the first place. And so maybe we just treat it all in the back end. And I said, that's a perfectly fine strategy. That is just absolutely not Laura. Like that's the opposite. And so it's like a doctor saying, well, we can fix broken legs all the time. So we'll just let them break their legs and then we fix their legs. You can choose to do that, of course, but that is not what makes good ethical health physics. So I was explaining, look, it's my job to try. I have failed if that is like if they get the cancer from the exposure, you're now like patching up my failure. And they didn't see it that way because they saw this all as one broad medical thing. So cataracts was obviously the limiting factor. ICRP just went to what 20 millisiever a year. And if I'm remembering that right. And yes, I mean, yes, it's so sensitive. That's going to be, especially, I will say, commercial providers don't have the same sensitivity for controls over the windows that NASA does. So the regular light intensity is such that you could just fry your retina, but the windows are big sales points. So they actually want the passengers to be able to open the windows. And so yes, there's UV coating on it, but there's still stuff coming in. So I think we're going to expect UV doses and things that are not currently being measured like the low energy X-rays that are going to be coming off the skin from the electron doses on the outside when they're close because again it's really a shockingly small amount of aluminum that makes those pressure vessels. So all that to say, yes, there was baseline for cataracts. There's talk of increased surveillance for the people who are flying repeatedly and um, yeah, it's still a lot of Wild Westy. Did I answer your first question?
Yes.
Yeah. Thank you.
All right. Ben, there are, I think, two questions in chat. The first is from Sean Austin, and his question is, do Virgin Galactic and Blue Origin have HPs on staff? Any info on those two people who have flown on their spacecraft?
Yes, to my knowledge, I know for a fact that Virgin Galactic does not have an HP on staff. It's just a technician, and they outsource any health physics. And again, they're only in space. They're at low altitude comparatively, very low altitude, and they're only up there for a handful of minutes. But they outsource it to Kent Tabisca and crew at Space Environment Technologies. They're out of well, just outside of LA. And so they fly. Uh, they use the Teledyne chip as the backbone for an RMOS radiation monitoring system that's now flown on a bunch of aircraft and also been on space station and a few satellites. So I know they're doing that. So they're actually, I think, doing very well, despite not having. I mean, I would love to be a health physicist involved with them. And Blue Origin, to my knowledge, does not. Axiom was the only one. Bigelow and Axiom were the only ones that bothered to have a health physicist at all. And what got me in the door actually wasn't the human part. It was the protecting, the overall radiation environment to make sure that the hardware would actually survive. And then the humans were, I won't say an afterthought, but a secondary thought. Axiom was the first that said, well, we really need to be putting some radiation in our crew quarters like NASA does, so we should have someone come in to help us do that. And they didn't know what they didn't know, so they thought it would just be an engineering project. And here I was educating them on the fact that this is an environmental characterization project. It's a regulatory project. It's a big deal. Um, so yeah, to my knowledge, there there are not a lot of people hiring health physicists, but that might all change.
Thank you. The second question in chat is from Gregory Smith. What dose limits have been used in the past space flights or missions?
Great question. So NASA used to have a dynamic set of dose limits, and they actually made a risk-based dose limit based on age and sex. And it was 3% REID, risk of exposure-induced death. So there was a big calculation, algorithm that they would take an astronaut's baseline information and their age and sex, and they would work that through and they'd say, okay, what's the maximum dose you can get across your career starting at the age you are now, along with the age you will be then, accounting for age effects also, and what shakes out to 3% for you. Now, that caused a lot of problems culturally in NASA because, according to the Japan cohort studies, women have a higher dose response than men. And so, what that meant was women dosed out of NASA sooner than men did. And while I would argue, and the NCRP argued that that is actually good health physics, we're keeping the risks equal. It actually is equal. All they were seeing is unequal opportunity to fly. And it got very contentious even when I was at Axiom with Peggy Whitson, who I think I can, well, maybe I shouldn't say that. Let's just say there were discussions had. She left NASA because she had reached her dose limit and she wanted to be sure that would never happen to her again as a condition of her joining Axiom. And so she is continuing to fly. So the dose limits, all that to say, um, internationally, it's 1,000 millisievert in a career, and NASA has moved to what they see as a more equitable opportunity limit, which they took the reference 35-year-old female and just drew a straight line across for everybody and said everyone has a ceiling at 600 millisievert career. So that's 60R. Am I doing that right? Yeah.
Thank you.
Sure.
Let me see. Bill.
Thank you. So yeah, the second question, I don't know if I'm going to end up phrasing it like a question, but so we haven't really talked about Mars, right?
Yep.
It helped me understand because nobody is talking about this at all when they're talking about Mars. Everybody's going guns blazing, and
Yep.
it's going to be a one-way trip, et cetera, et cetera. Well, I'll tell you what, that strategy of increased monitoring isn't going to work well for that, right? So, are they just ignoring it? Is it just that the media isn't picking up on it? What are people thinking? Like to the extent that you're on the pulse there.
Yeah. Excellent question. So Mars is the worst of both worlds from a radiation perspective. So down here on Earth, right, we got a nice thick atmosphere. We've got some slowdown from the magnetic field, and then the cosmic comes in and hits the atmosphere, and we get a rain of secondaries coming down, and then eventually there's a little neutron trickle down here at the ground. But if you go to the altitude of the International Space Station, which is about 250 miles, there's actually a lot of backscatter neutrons that are coming off the Earth's atmosphere and hitting the station, going back out to space. So the being in low Earth orbit isn't quite as friendly as people assume it is. There's not a perfect shield just because the magnetic field is there. So I'm saying that as context. Whereas if you go to the moon, well, you're naked before God and all radiation in the cosmos, except 2 pi. Like the moon is actually blocking half of it, the rest of the cosmos underneath you, but you do get that backscatter neutron problem. Um, from the lunar regolith bouncing back out and coming through you. So you get cosmic from above and then neutrons from below. Wow. Enter Mars. Mars so Mars's atmosphere is so thin that it will let the cosmic come all the way in and just like the moon and hit the ground and you get backscatter neutrons. So you're getting primary hitting you, and you're getting secondary neutrons coming out. But there is actually a little atmosphere, so that it does mean you're also getting downscatter neutrons. So you're getting primary coming down, and secondary coming up through you. So it is the radiation worst of all worlds. And that's not to talk about the dose incurred during the transit from here to there. So what are people talking about? None of that actually peaks you up into acute radiation syndrome territory. It's just really high compared to anything that we consider even close to normal
But
now.
but there's a lot of unexplored endpoints too, right? I mean,
Oh yeah. Yeah, you mean
with
room for unexpected surprises in
yeah,
turn.
yeah, or like cardiovascular degradation
Yes.
and things like that, right? Like that's going to affect the mission.
Yes. And so I, I will tell you that the the health physicists I know, so I worked with a guy at Axiom who just came from NASA SRAG, so we had a lot of heart-to-heart talks about the pulse at NASA and then how it was different or the same in commercial world. And they're the people who are most conservative are being kind of driven out as being, it is my hot take, are being kind of driven out from NASA for being seen as anti-flight or anti-human flight. So there is a line to walk, even at NASA, in being cautious and being protective, and then suddenly being seen as anti-flight. And so I think what you're left with is more permissive health physicists who are saying, hey, we got a boat, they do gap analyses, and they say, we got a boatload of unknowns here, and it's not looking great for cardio and cognitive and, central nervous system and all this stuff. And NASA turns around and says, that's why this is um, exploration. These are all test flights, not routine flights. And so, I guess the shorter answer is NASA is knowingly asking their astronauts to be radiation guinea pigs for these missions, and the astronauts are apparently okay with it.
And I think that's a fair answer. I mean, it's hard to argue with it, really, honestly, when you talk about what we're actually doing.
Yeah,
Appreciate the answers there. By
sure.
the way,
Great question.
if you want to come back to RSL in time for the 2028 Dragonfly and Rosalind Franklin missions, we got room.
Yeah, I'll keep that in mind.
Thanks, man.
Sure. Thanks, Bill.
Nice. Good questions. Um, that's all the questions I see in chat or raising hands. Are there any last question for Ben before we conclude this session? All right. So hearing none, thank you, Ben, for this great presentation and for joining our virtual meeting. And we hope to see you in our next annual meeting to next month. And I would like to thank our treasurer Coresa for arranging this virtual meeting, for setting up the Zoom and running this meeting. So it was a great presentation, and thank you, Ben, so much again. And thank you all for joining us for the session.
Thank you all, and thank you so much for the opportunity.
Thank you. And we hope to see you all in our next annual meeting next month. So have a good rest of evening and bye-bye.